This is an A-level core pure question, complex numbers and sums of series. The infinite series C and S are defined by C equal to cos theta plus half cos 5 theta plus a quarter cos 9 theta plus an eighth cos 13 theta and so on, and S sine theta plus a half sine 5 theta plus a quarter sine 9 theta plus 1/8 sine 13 theta and so on. Given that the series C and S are both convergent, part A, show that C plus IS is equal to 2e to the power I theta over 2 minus e to the power 4 I theta. Okay, now there are different ways of doing this question, but I'm just going to show you one way and a way that I prefer to do it. So the first thing that I'm going to do is I'm going to put together C plus I times S. So I need to multiply S, all of these terms, by I. So if I write that down, I'll have C plus IS is equal to cos theta plus, now what I'm going to do, I'm going to group together pairs of terms. So those two are going to go together, these two are going to go together, and so on. They seem to go in pairs because the number in front of constant is the same, and like the powers of theta are the same. So because these are all going to get times by I, I've got cos theta plus I sine theta. So that's the first two grouped together. I've done those two. And then plus a half, and group these two together, and that'll be cos 5 theta plus I sine 5 theta. So I've done those two, and then I'll move on to the next two, group those together. So that's plus a quarter cos 9 theta plus I sine 9 theta. So I've done those, and then I'm just going to group together these last two here. So plus 1 over 8 cos 13 theta plus I sine 13 theta. And then plus dot dot dot, because it goes on forever. Now I can use an identity to change these, and that identity is if I have cos n theta plus I sine n theta, I can write that as EIN theta. So that's going to allow me to write each group of terms in exponential form. And the reason I'm doing that is because what I want to get to is in exponential form. So if we do that, the first pair here will just become e to the I theta, n is 1, so e to the I theta. Then the next term is half, and then this will become e to the I 5 theta or 5I theta. I'll put the I first, then a number afterwards, like that. And I'll keep going. The next pair, a quarter e to the I 9 theta, and then 1/8 e to the I 13 theta, and so on. This is an infinite series which I want to find the sum of. So if you want to find the sum of a complex infinite series, you need the first term, w, over 1 minus z, which is the common ratio. So if we have a look at this, the first term is e to the I theta, so e to the I theta, and z, the common ratio, is going to be a half, because you can see you multiply it by half, and because the power goes up by 4 theta each time, we're also multiplying by e to the I 4 theta or 4I theta. So the next step now would be to write that this infinite sum here is going to be equal to e to the I theta over 1 minus a half e to the I 4 theta. Now we've almost got what we want. We need to get this, and the way to get to that last step there is just to times the top and the bottom of this fraction by 2, and if we do that, we'll get 2 e I theta, and that's over, that'll become 2, then the half goes minus, and then e, now I've written it as I 4 theta, always write it in the form that they have, so we'll just swap the 4 and the theta around, and then we get exactly what they want as required. Part B, hence show that S is equal to 4 sine theta plus 2 sine 3 theta all over 5 minus 4 cos 4 theta. Because we have hence, that means use what we worked out in part A, or proved in part A, which is what I've got here. And I notice that S is equal to the imaginary part of C plus IS. So what I want to do is to work out what the imaginary part of this is. So S will be equal to the imaginary part of 2e I theta over 2 minus e 4 I theta. Now, to get the imaginary part of what I've got here, this expression here, I really need a denominator that's either real or imaginary, because at the moment all the real and imaginary parts are all sort of mixed up. And a trick we can use to do that is to think carefully about what we can multiply the top and the bottom by to make this denominator real or imaginary. And a little trick that we can use is that we multiply the top and the bottom basically by this denominator, but we change the sign of e to negative, because then when we multiply like the e to the 4i theta and the e to the negative 4i theta, they're going to cancel out. So we want to multiply by 2 minus e to the negative 4i theta over 2 minus e to the negative 4i theta. Now if we do that, what we'll get is S is equal to the imaginary part of, now we'll do the multiplying out. So we'll multiply each term at a time. So 2 to the e I theta times by 2 will be 4 e I theta. And then when we multiply this term by this term, then we'll have negative 2. Now when we multiply, what we need to do is add the powers. We've basically got one lot of I theta, and then we need to subtract 4 lots of I theta, which will give me negative 3 I theta. So you've got e to the negative 3 I theta. And that sort of makes sense because I can see the 3 theta there and a theta there, so it seems to be matching up. Okay, now we'll do the denominator, and this is like the special part that's going to simplify this denominator. So we'll do 2 times 2, which is 4. Then we'll do 2 times by the negative ei negative 4i theta. So you get negative 2e to the negative 4i theta. And then we'll times this by 2. So this will be minus 2e to the 4i theta, like this. And then the bit that's going to turn it into something real here is when we do negative ei 4 theta times by negative e to the negative 4i theta. That will become e to the 0, which is just going to be 1. So I'm just going to be put a plus 1 at the end. Just going to make my denominator line, fraction line, a little bit longer, like this. And my next step now is just going to be to tidy up this denominator. So I've got 4 plus 1, which makes 5. That's promising because we have a 5 here. Then I'm going to factorize these terms here. You'll see why in a moment. So I'll have negative 2. And then I'll have e to the 4i theta plus e to the negative 4i theta. So I've just swapped the terms around for a reason. Okay, so that's our denominator. And then for the numerator, I'm going to leave it as it is for the moment. And then I'll make the changes. So minus 2 e to the negative 3i theta. Now we've got another identity which we can use to deal with this part here. So all of this in the bracket here can actually just be written as 2 cos 4 theta. So we'll do that next. and then I'll deal with the numerator as well. So 4 e I theta, using the identity again with sine and cos that I did in part A, and I'll write that down as well. So cos n theta plus I sine n theta is going to be equal to e I n theta, like this. So that means that this can be written as 4 cos theta plus I sine theta, and then minus 2, so we've got to this bit here, and that can be written as cos of negative 3 theta plus I sine negative 3 theta. And now my denominator I can write as 5 minus 2, and we've got up to this bit here, of 2 cos 4 theta. Now the denominator is real, so the imaginary part of the whole expression is going to be the imaginary part of the numerator. So I'll just highlight that what those terms are. So 4 cos theta is going to be a real part. I want the imaginary part, so 4 I sine theta, or just 4 theta, or 4 sine theta, sorry, is going to be imaginary, and then minus 2 times by sine negative 3 theta is also going to be imaginary as well. So let's make a little bit of space, and now we can turn our attention to working out the imaginary part of the numerator. So s is now equal to 4 sine theta, okay, that's imaginary, and minus 2 sine negative 3 theta, sine negative 3 theta, probably deal with that in a moment. And then in the denominator, 5 minus 4 cos 4 theta. So from there, what we can do is this negative 3 theta, sine negative 3 theta, it is the same as it moving the minus sign to the front. So we get 4 sine theta plus 2 sine 3 theta all over 5 minus 4 cos 4 theta, and it looks like we've got the result as required.